So hello everyone. Today we will be looking in the week 5 of uh, the course NMR that is currently running. So in week 5, I would like to give a brief overview of the topics that we have learned in week 5. So the topics are NOE, nuclear Oberhauser effect, which comes under the polarization transfer techniques. And in nuclear Oberhauser effect, there are two types. There are two types of NOE we have studied. Then, apart from NOE, we have also covered inept, depth, and rosy. So, we'll be trying to look at the key concepts that have been covered in this week, and also we'll from those concepts we will try to solve some of the questions related to this week's topic. So I'm Akashjyoti Pathak. I am uh, I'm a student, PMRF student in NMR Structural Biology Lab in IIT Bombay. So I am your course TA for this course. So I'll be sharing my slide. Okay. Okay, so we will start. So the first concept that was discussed in this week, it was related to the last topic of last week's lecture, that is the polarization transfer, and it is also known as nuclear Oberhauser effect. So we in the last week's class, the only the nuclear Oberhauser effect, what it was mentioned, and further details on it was not covered. So this week, the nuclear Oberhauser effect has been discussed in detail. So we'll first look into the key concepts in this topic. So nuclear Oberhauser effect, or NOE for short. So it can be defined as a change in the intensity of one NMR resonance line when another resonance line in the NMR spectrum is in some way perturbed, say by saturation, inversion by a pulse. So these are the techniques in which the nuclear spin of one of the nuclei can be perturbed by another nuclei. So the essential condition for this to happen is that the two nuclei must be in some kind of interaction. So the interaction in which these two nuclei are kind of get connected with each other is known as dipolar interaction. So the dipolar interaction between the two nuclei that helps in manipulating the population difference between different energy levels in a given system of spins. So as we know that in NMR, the signals that we see, those are the intensity signals. And those intensity signals are a result of the population difference that exists the two energy levels when when the sample is subjected to an external magnetic field. So that we have already learned in the earlier classes that when under the external magnetic field, the nuclear spin it splits. It splits because of Zeeman effect into lower energy spin state and a higher energy spin state. The lower energy spin state, we know that it is alpha, and the higher energy spin state it is known as beta. So what is being said here is the polarization transfer. What is happening is there are two nuclear systems. Okay. So say there are two nuclear spin systems, A and X, and these two nuclear spins are coupled to each other. These two nuclear spins are coupled to each other. And how are they coupled? By dipolar interactions. They are coupled to each other. What is dipolar interaction? We know that uh, these nuclei they act as dipoles. Why do they act as dipoles? Because they have charge associated with it. They have magnetic moments. They have an associated magnetic moment to it, and that magnetic moment gives it makes them behave like small magnets. Makes them behave like small magnets, and because of this magnetic property of the nuclei, they behave as dipoles. And since these nuclei are close to each other, since these nuclei are close to each other and they have comparable magnetic moments, they have very similar magnetic moments. So, towards proximity to each other, then the nuclear spin of one of the nucleus gets transferred to the another nucleus. And why does this happen? Because we we excite. We specifically in this experiment, the nuclear polarization, the polarization transfer of the NOE experiment. In that experiment, we excite a particular nucleus with a radio frequency pulse. So when this radio frequency pulse is uh, is irradiated on this particular nucleus, say the nucleus of A, then what happens? The population difference. There is a population difference between the two energy states, the lower energy state and the higher energy state. So because of that, the the nuclear spins they go to the higher excited state. Now, since the equilibrium state of this nucleus A, it is perturbed. So what happens? It tries to come back to its equilibrium state once the radio frequency pulse is stopped. So during the relaxation process, the uh, the radio frequency pulse with which the nucleus A is excited, it transfers that energy to its nearby nucleus, to the nucleus which is having a magnetic moment very close to it. So in this case, it is X. So that way, what happens when it relaxes? That is known as spin lattice relaxation. During relaxation of the nuclear spin of A by way of spin lattice relaxation, the this, the energy is transferred to a nuclei which is in its close proximity, say X, and that way, what happens? This X that gets excited, and there is a population difference. The population difference is seen in the nuclear energy levels of the nucleus of X. Okay. So we'll mm, it's a polarization transfer refers to the process with the Polarization transfer refers to the process where the polarization of one nuclear spin is transferred to another nuclear spin. So the polarization transfer is also known as the nuclear Overhauser effect, and this arises due to dipolar interactions between the two nuclei. So whenever a nucleus is perturbed from its equilibrium state, the perturbation is transferred to its neighboring nucleus via dipolar interactions. And this provides a mechanism for the relaxation of the perturbed nucleus. So as I have just explained, so say that nucleus A is excited by a radio frequency pulse. So when it comes back to its equilibrium state, then it transfers the nuclear spin to another nuclei with which it is in dipolar interaction. So by way of transfer, it is able to relax to its equilibrium state. And so this is given by this equation. So eta I s is equal to I minus I0 by I0. So what is eta IS? It is the NOE, nuclear Overhauser effect at resonance I due to a perturbation at resonance S. I0 is the intensity of the resonance I in the absence of the perturbation, and I is the intensity after the perturbation at S. So what is being said here is that there are two nuclei. So say this is the intensity of the nuclei, and this intensity is at I, and another nucleus is there which is in its close proximity, and this nuclei intensity is at position S. Okay. So I0 is the intensity initially. This is the intensity when there is no perturbation in the nuclear spin of the nuclei of this nuclei. So when the nucleus is perturbed, when the equilibrium state of the S nuclear spin that is perturbed, then its intensity, since these two nuclei are in dipolar interaction, so there is the intensity of this nuclei changes from I0 to I. Okay. So based on this concept, we'll be discussing the first question. So the first question is, polarization transfer between the nuclear spin is caused by. So there are four options. First is J coupling. Second is coupling with the magnetic field, coupling with the radio frequency, dipolar coupling between the spins. So what should be the answer of this question? So the answer should be option D, right? Dipolar coupling between the spins. Why? Because as we have already studied, this dipolar coupling is an interaction between two nuclear spins that arises due to the magnetic dipole-dipole interaction between them. The coupling is dependent on the distance. So it is a distance dependent process. And generally, the distance between the two nuclei should be some 5 angstrom for this polarization transfer to take place. And not only the distance, but it also depends on the orientation of the two nuclei. How are they oriented with each other and with respect to the external magnetic field? So what is this dipolar coupling and polarization transfer? So in the context of polarization transfer, dipolar coupling allows for the transfer of magnetization from one spin to another because it directly affects the population of the nuclear spins in the energy levels and transition probabilities of the spins involved. So during the relaxation, what happens? The nuclear spin is transferred from one nucleus to another, and that affects the population of the nucleus to which the magnetization is transferred. Okay. And actually, it is dependent. We will see in the later part of our discussion that it is also dependent on the whether the transfer, the polarization transfer will happen or not. That is also determined by the transition that takes place when the two nuclei are coupled to each other. But what type of transitions are possible, what are not possible, we'll discuss it shortly. So the interaction is distance dependent and is most significant when the nuclei are close to each other. Dipolar coupling is responsible for the transfer of polarization in NOE experiments, which is one of the primary methods. So since it is a distance dependent phenomena, so we can exploit this phenomena to measure the distances between the two nuclei. From the signals that we will be getting, we can determine whether there is any change in the intensity signals. So if there is a change in the intensity signals, then we can say that these two nuclei are coupled to each other. Okay. So I not the other options. So other options are about J coupling. So J coupling, as we have already learned in YOTS week two lecture series. So J coupling also causes the interaction between nuclear spins, but it does not lead to polarization transfer in the same way as dipolar coupling. So in that we learned that there was the concept of equivalent nuclei and non-equivalent nuclei. So in the presence of non-equivalent nuclei, the splitting of the nuclei happens. The adjacent nuclei happen. And in that, we also learned the Pascal's, the splitting happens by way of Pascal's triangle. So J coupling is through bond coupling. So unlike polarization transfer or NOE, which is a space which happens in space, it is a spatial dependent process. It is not happening through bond. J coupling is seen when the two nuclei are attached to each other by covalent bond. Okay. By covalent or there should be some bond between the two nuclei for the J coupling to happen. And also this influences the splitting patterns in NMR spectra rather than direct polarization transfer. Okay. So in case of J coupling, we saw that in presence of a non-equivalent hydrogen, this non-equivalent hydrogen has the potential to split this, split the intensity of this nuclei into 2i plus by way of that rule 2i plus 1, 2 into I plus 1. In that way, it can split into two multiplets or singlet or quadruplet. Okay, but in this case, in case of polarization transfer, there is no splitting which is observed. Rather, there is only change in the intensity uh, of the nuclei in which the dipolar coupling exists. So either the intensity will increase, the intensity signal, either it will increase or it will decrease, Okay. But no splitting of the intensity peak is seen in case of NOE. Okay. Now coupling with the magnetic field. So what does it tell? So this is a general interaction of, so when a nucleus, when a sample is introduced into a strong external magnetic field, then we have learned that because of Z-band interaction, the nuclei of the nuclei of the sample, they split into two energy levels. One is the uh, higher energy level, higher spin state or beta. Another is the lower energy spin state, alpha. So this splitting is because of Z-band interaction. But it does not cause polarization transfer between different nuclear spins. So it is completely different from the polarization transfer uh, or NOE effect. Coupling with RF. So why is this option wrong? So this refers to the interaction of nuclear spins with the amplified radio frequency field during NMR experiments. So when RF pulses are used to manipulate the magnetization of while RF pulses are used to manipulate the magnetization of nuclear spins, they do not inherently cause polarization transfer between different nuclear spins. Okay, so it is what this is the basis of resonance in nuclear magnetic resonance. So when the radio frequency pulse, the frequency of the radio frequency pulse matches with the frequency of the nuclear spins, then there is then the orientation of the nuclear spins it changes. Okay. Now we'll move on to the second question. So the second question is negative NOE occurs because of. So the four options are domination of single quantum transition probability. The second option is domination of double quantum transition probability, domination of zero quantum transition probability, or slow molecular motion. So which option will be correct? It will be because of negative NOE will be because of the domination of zero quantum transition. Right? Why? Because the magnitude of the NOE is proportional to the difference in the two relaxation rates, which is referred to as the cross relaxation rate or sigma. And this sigma is given by W2 minus W0. So this is W2. W2 is known as W2, or it is also sometimes called as omega 2. The W2 is known as the double quantum transition probability. This is the double quantum transition probability. And W0 is zero quantum transition probability. Okay, so if W0, the probability of this transition, that is W0, that is if W0 is greater than W2, then the net magnitude of this sigma also known as the cross relaxation rate sigma, this will be negative, and the overall this process will be known as negative nuclear Oberhauser effect. And if the W2, that is the double quantum transition probability, that is greater than W0, then sigma will be positive. So we will try to understand what exactly is this double quantum transition probability and zero quantum transition probability. Okay. So so 1 minute. Thanks. Okay. So we all are familiar with this diagram. So dipolar interaction, it always happens. It is seen between two nuclei which are in dipolar interaction with each other. So say we are looking into a two spin system which are coupled to each other, which are coupled to each other by dipolar interactions. Okay. So the two spin system, let us consider an AX nuclear spin system. AX nuclear spin system. So what is this AX nuclear spin system? So A is one nucleus and X is another nucleus. And these two are coupled to each other by way of dipolar interactions. So in this case, what will be the energy level diagram of this two nuclei interacting system? So we know that we are already familiar with this energy level diagram. So any nucleus, it can exist. The spins of the nucleus, when subjected to an external magnetic field, it can exist in either of the two states. That is either the lowered energy spin state or the higher energy spin state. So that is alpha or beta. So say this is the alpha spin state. So alpha spin state means at this energy level, both the nuclei of A and the nuclei of B, both are in alpha spin state. Another can be alpha beta. Alpha beta spin state. So here, what is happening? 1 minute. So beta alpha spin state means that A and X. Okay. So the first spin state that we will write, that will be referring to the spin state of the A nucleus. And the second spin state that we will be writing, that will be referring to the spin state of the second nucleus. So in alpha, it means that the nucleus of A is in alpha spin state. The nuclei of this A nucleus is in alpha spin state, and X nuclei is also in alpha spin state. In beta alpha, the nucleus of A is in beta spin state, but the nuclei of X is in alpha spin state. It can be, or it can be what? Alpha beta. So in this case, the nuclear spin of A is in alpha spin state, but the nucleus of X is in beta spin state. Or it can be beta beta. Okay. So let's connect these four energy states, because when a radio frequency pulse is applied to this dipolar, this two spin nuclear system, then under the influence of the new radio frequency pulse, and since they are coupled to each other by dipolar interaction, the nuclei between these two spin states the nuclear population between these two spin states can exchange with one another because of the transfer of energy from A to X or X to A. Okay. So let's say that the population, the population of alpha spin state, that is P1 population of the nuclei in the alpha spin state. That is the net total population is P1, and the population in this beta alpha spin state, that is P2. In alpha beta, so it is P3, and at in both the nuclei and beta beta spin state, that is P4. Okay. So at equilibrium, what will happen? At equilibrium condition, at equilibrium condition, Okay. At equilibrium condition, you will see that, let's say that in equilibrium condition, there is a population difference between these spin states by a uh, by a difference d, by difference d. Okay. So now what is the population in each of these energy states? So if it is P1, okay, so if this is at a higher energy state, and the population difference that I said existing between the high energy state and the low energy state, that is what? That is D. That is D. So if this is P1, this will be the population, the total population in this beta alpha energy spin state. That will be P1 minus D. Okay. And here the population was how much? P3. And the population is P3, and at higher energy state, higher energy spin state, beta beta, the population difference, there will be less population in the equilibrium state. So that population difference between the higher and the lower energy spin state, that is D. So it will be what? P3 minus D. Okay. So now what happens? That in this dipolar, uh, in this polarization transfer experiment, so in polarization transfer experiment, what do we do? We excite our system with a continuous saturating radio frequency pulse. Continuous saturating radio frequency pulse. And then this is what? This is the continuous saturating. We'll come to know why it is called saturating in a short while. Saturating RF pulse. So we excite the two nuclear system with a continuous saturating RF pulse, and after the saturating pulse, we excite the system with a uh, with a 90-degree X pulse. So this pulse has been 100 X pulse is applied in the X direction, and then we acquired the signal, acquired the FID signal. Okay, so during this phenomena, what happens because of this saturating pulse? What happens is the population difference. There is a change in the population difference between the different energy states. So because of this, because of the saturating pulse, the population difference, the population difference is under the influence of this continuous saturating pulse. We try to saturate the populations. We try to saturate the populations that are existing in the different energy levels. So what happens is that the population difference becomes zero. The net population difference between these spin states, it becomes zero. So what happens? There is a distribution of the population, redistribution of the population of the nuclei between these two energy states. So what happens is the population in this lower energy state, it reduces by d by 2, and if the total population difference was d, so if the population here is it reduces by d by 2, then here it will be P1 minus D by 2. Okay, so the net population difference, the D, that gets redistributed by half and half in these two energy levels. Similarly, here also, what happens is this gets under this as saturating RF pulse, it gets redistributed. And so what happens here also, the population difference 3 minus V by 2 becomes saturated. Okay. So what is this? This was what? This was alpha alpha spin state. This was beta alpha. This is alpha beta, and this was beta beta. Okay. So this is what transition is taking place here. The alpha is changing to beta. Okay. So this is known as what? A1 transition. A1 transition, because the nuclear spin state of the A nucleus, that is changing from alpha to beta. So that's why it is denoted by A1 transition. A1 transition. And if we look here, from alpha beta to beta beta. So here also what is happening? The A spin state, alpha A spin state is changing to beta. So this is denoted by A2. Okay. So the net transition of the A nucleus spin system, that is A1 and A2. Similarly, if we look in this into this two energy states, alpha alpha and alpha beta, this one, then this the second alpha spin state, that is changing from alpha to beta. So here the transition is happening in the X nuclear spin system. So this is denoted by X1, and if we see this beta alpha to beta beta, then the alpha spin state of the X nucleus is changing from X alpha to beta. So this will be denoted by X2. Okay. Now we know that this can be also referred to as alpha change to beta alpha. So this is the net change is how much? The net changes is from, this is alpha means minus half. So -1 to, this is beta alpha means 0. So this the probability of this transition, okay, from this alpha alpha to beta alpha, that is denoted by omega 1. And this is known as what we earlier referred to as the uh, single spin probability transition. Okay, zero spin, double spin, and single spin. We referred in the in our earlier slide. So since it is the changes by a factor, this from -1 from 0 from the difference is 1, so it is known as the probability W1, the probability of transition from alpha alpha to beta alpha, probability of transition. This probability of transition is known as single quantum transition probability. Single quantum transition probability. Okay, probability. Okay, and this transition is being seen in the A nuclear system. So in the superscript, we write A. Okay. Similarly, if we look in the into this transition where beta alpha is changing to beta beta, then here also the net changes by the magnetic moment. The net magnetic moment is changing by 1. So this is beta alpha is 0 and beta beta minus plus half, uh, minus minus half. So that is -1. So the difference is, so alpha is +1 and beta beta is -1. So the net changes, how much net magnetic moment change? If we see, that is by 1. So here also we call it what? Single quantum transition probability. And since the transition is seen in the X nucleus, so it is in the superscript we write X. Okay. Similarly, here also alpha to alpha beta. This is also single quantum transition, and it is denoted by W1 because X is from the second alpha is changing to this second beta. So this is omega 1 X. Okay. And from alpha beta to beta beta, this is omega 1 A. Now if we look into this transition where alpha beta is changing to beta alpha. Okay, that is, if we look into this clearly, alpha beta changing to this transition from alpha beta to beta alpha. That is the nuclear spin state of the A nucleus is changing from alpha to beta, and the X nuclear system is changing from beta to alpha. So here it is zero. The net magnetic moment here it is zero, and here also it is zero. So the net this probability of transition, it is known as zero quantum transition probability. So this is, it is denoted by omega zero, and it is called what? Zero quantum transition probability. Transition probability. Okay, and if we look into this transition, that is the transition from alpha alpha, this alpha alpha to beta beta. This transition, this one. Then this is how much? Alpha alpha to alpha beta, to beta beta. So this was one, yeah, plus half. So this is one plus one, and this is minus half and minus one. So the net changes. The net changes two. Okay, one minus of minus one. So two. So this is denoted by omega two, and this is called as the double quantum transition probability. Double quantum transition probability. And probability. Okay. So we got the terminologies clear. Now let's try to understand what is happening due to the application of this pulse. Okay, what is the change in population that is taking place in each of these energy levels? Okay. So we'll take another slide. So due to the application of the saturating pulse, the population of the nuclear spin population, it changed, right? So, so it changed, this one changed from P1 to P1 minus D by 2. So the net population here is P1 minus D by 2. Here also it is P1 minus D by 2. Here it is P3 minus D by 2. And this is P3 minus D by 2. Okay. So okay. So now this is what? This is A1 transition. This is A2 transition. This is X1 transition, and this is X2 transition. Now, since will there be, will we be seeing any intensity in the signal? Will the signal, will we see a signal intensity because of A1 transition? Will we see a signal intensity because of A1 transition? We won't, right? Because the population difference, because of the saturating RF pulse, what has happened? The population difference has become zero. So this higher energy state, this is also at a population of P1 minus D by 2, and the lower energy state, that is also at a population of how much? P1 minus D by 2. So the net population difference is net population difference associated with A1 transition. Okay, A1 is what? A1 is transition. This is the transition P1 to P2. Right. So 1 to 2, we can actually number these to understand it better. So we'll number these transitions. Okay. This will make things more clear. So this is one. This is this energy state. Let us label it as one. This is the second energy state. This is the third energy state, and this is the fourth energy state. Okay. So this 1 to 2 transition. Okay, the A1 transition. So here the population difference is 0. So we won't see any peak in our NMR signal because we have learned in the very basics that it is the population difference. It is the population difference only, which due to which we are see which due to which we are able to see a peak in our signal. Okay, that difference in the population, that is what contributes to the peak in NMR signal. So since there is no population difference, so they won't see any signal due to A1 transition. Similarly, in case of A2 transition, A2 is what? 3 to 4. 3 to 4 transition. We here also we won't be seeing any peak in our NMR signal because here also the population difference is 0. P3 minus D by 2. If we do this, P3 minus D by 2 minus P3 minus of minus D by 2. So plus D by 2. So the net result is 0. So the population difference is 0. So these A transitions will not lead to any, will not lead to any NMR signal. NMR signal. Okay. Now here, if we consider the X transitions. So X transitions are, what are the X transitions? X1 and X2. Okay. So X1 transition is from 1 to 3 and X2 transition is from what? 2 to 4. 2 to 4. Okay. So if we check out the 1 to 3 transition, then this X1 transition, then the population difference is P1 minus, so X1 is equal to P1 minus D by 2 minus P3 plus D by 2. Okay. So these will cancel and we will get P1 minus P3. Okay. Similarly, here also X2, what will be the difference in population? Difference in population will be P1 minus D by 2 minus P3 plus D by 2. Okay. So here also we are getting P1 minus P3. So the population difference in X1 and X2, okay, that is equal, and that is equal to P1 minus P3. Okay, P1 minus P3. Now, if we compare it with the equilibrium condition, if we compare it with the equilibrium condition, what was the equilibrium condition? Equilibrium state. In equilibrium state, what was the population in each of these energy states? Do you remember? So the population was, this was P1. This one was P1 minus D by 2. This was P3. And this was P3 minus D by 2. Sorry. Equilibrium means when the saturating RF pulse was not applied. Okay. So when the saturating pulse was not applied, then the higher energy was efficient in the number of nuclei by D. Okay. So P1 minus D, and this another higher energy level that is P3 minus D. Okay, so now this was what? This was X1 transition and this is X2 transition, right? So here also in equilibrium condition, if we look at the population difference in this X1 and X2, then what will we see? Then we will see that X1 is equal to how much? P1 minus P3, and X2 is equal to also how much? P1 minus D minus P3 plus D. So here also P1 minus P3. Okay. So both under this, both under both the conditions, at equilibrium condition as well as at perturbed condition. Okay. When we are perturbing it with radio frequency. So after the application of the perturbation, then also we are seeing that the population difference in this X1 due to this X1 transition and the X2 transition they remain the same. Here also P1 minus P3. This was equilibrium. This is equilibrium condition. Ah, and here X2 is equal to, this is equilibrium. The equilibrium. So that is how much? P1 minus P3. And when the say nucleus is perturbed, nuclear system that is perturbed, here also we are seeing that the population difference is P1 minus P3. So when we will be comparing the signal that we are getting in the equilibrium condition and when we are perturbing the nuclear system, then we won't see any difference in the nuclear signals. So initially we were seeing uh, uh, a signal like this, and after the perturbation also the intensity of the signals that will be remaining the same. Okay, so there won't be any. So that is not our purpose, right? Our purpose is to enhance the signal, enhance or either enhance or decrease. So there should be some change in the signal due to the perturbation. So how can we achieve it? So, one minute. Okay. So now we need to know, we will see how we can perturb the signal. Okay. So that we get a difference in the signal upon the application of the radio frequency pulse. Okay. Now, now we must not forget that after the radio frequency pulse is applied, the these nuclei will start to come to the equilibrium state. Nuclei will start to get back to their equilibrium position. Okay. So what will happen is now during the relaxation process, during the relaxation process, uh, so during the relaxation process levels, the energy levels whose whose population are higher, whose populations are higher than their equilibrium, than their equilibrium populations. Then during the energy levels whose populations are higher than uh, their equilibrium populations, they will lose they will lose the nuclei. Okay. we will lose the nuclei. That means during the relaxation process, the nuclei from those energy levels that will come down to the nuclear energy levels where at equilibrium state the population was lower. Okay, will lose, and those energy levels, where the population is less in the equilibrium state. Okay, population is less in equilibrium state will gain. Equilibrium state will gain nuclei. Okay, so this transition will happen, and this transition will lead to a signal in the NMR spectrum. Okay, so now what will happen is that so this one was uh, so we will look into the transition probabilities. Okay, so this was what omega 1a. This is also omega 1a. This is omega 1x. This is omega 1x. This is, and this is how yeah, oh, this is omega 0. This transition. This is omega 0, and this is from here to here. This is omega 2. Omega 2 of the double uh, double nuclei probability transition. Okay, so what will happen is this this will be here. What was the population? T by 2 plus T. Okay, here it will be P1 minus T by 2 minus T. Okay, and here it is P1 minus D by 2, and here it is P, P3, P3, P3 minus D by 2. Okay, so here if we are considering the W2 transition, W2 transition. So what will happen is this will be P1 minus D by 2 plus P minus P1 plus D by 2 plus uh, uh, minus P1 plus P. So this will be what? P3 minus D by 2, and this will be P3 minus D by 2 minus minus T. Okay. So this will be this will be pretty. So here it will be, this will cancel, and here we'll get P1 minus P3 plus T. Okay. So this will be referred to as omega 2 transition. Okay. And this will be referred to as omega 0 transition. Okay. Omega 0 transition. So when we are okay, so if we are considering the negative NOE, then we are looking into the difference between omega 2 and omega 0. So if omega 0 is so if okay, so if omega 0 is more than omega 2, then uh, there will be negative NOE. And if omega 2 is more than omega 0, then there will be positive NOE. Okay. Now we'll look into the next question. So next question is steady state 1H NOE is positive in large molecules, negative in large molecules, negative for small molecules, or does not depend upon molecular size. Okay. So here the option is what? Option B, negative in large molecules. Why? Because the positive NOEs generally occur in small molecules. In small molecules, we see positive NOEs, while the negative NOE is a common feature of macromolecules. Macromolecules are large molecules. So what happens in large molecules? There is a very efficient distribution of magnetizations by zero quantum transition processes among various nuclei within the molecule. So what happens? There is a very efficient redistribution of magnetizations by zero quantum transition processes. Zero quantum transition processes means this W0. W0 is known as the zero quantum transition processes. So there is very efficient redistribution of magnetization. Okay. So we know that from the earlier question, we saw that this sigma is equal to omega 2 minus omega 0. So here it is being said that we will see a very efficient redistribution of magnetization by zero quantum transition process. So W0 is more than W2. So therefore, sigma is positive. That means we'll call it as positive NOE. Okay. Whereas in case of small molecules, in case of small molecules, what is the scenario? The population changes, and hence the magnetization changes will have to occur by dissipative processes to the lattice by double quantum transitions. Okay. Will have to occur by dissipative processes to the lattice by double quantum transition. So so it does in large molecules. So in small molecules, what will be the case? In small molecules, we will see negative NOE. Okay, we will see negative NOE. Okay, so sorry. So here, what will be the here? Sorry, made a mistake here. So omega 0 will be greater than omega 2. Yes, and so it will be negative. Okay, it will be what? It will be negative. Okay, but in case of small molecules, there we will see positive NOE. Positive NOE because the W2 is large in case of small molecules. So since W2 is large in case of small molecules, so this sigma will be positive, positive, and therefore it will be called as positive NOE. So positive NOE in case of small molecules and negative NOE in case of what we'll see negative NOE in case of large molecules. Okay. So Thus, in large molecules, W0 is very dominating. Is a very dominating process leading to negative NOEs. Okay, so W0 is very dominating in case of large molecule. So this entire the net result will be negative, and it will be called as negative NOE. Okay. But in case of small molecules, W2 is dominating. W2 is dominating, and so it will lead to a net positive value, and therefore it will be called as positive NOE. Okay. So did you understand? So next, what is the question? Next question is, in an AX system, while saturating the A spin, the polarization gain by steady state NOE is proportional. Is we'll have to see. We have to tell the correct option. So the options are proportional to gamma A by gamma X, proportional to gamma X by gamma A, proportional to gamma A into gamma X, or independent of gamma A and gamma X. So what is this gamma A or gamma X? These are the gyromagnetic ratio. So gamma is the gyromagnetic ratio of nucleus A. Gamma X is the gyromagnetic ratio of nucleus X. Okay. So which is the correct option? Correct option is A. Okay. Why? So we will understand why. The answer is option A, because in an AX spin system where A and X are two different nuclei. So these are two different nuclei. For example, say the nuclei A, the nucleus A, it is of hydrogen, and say the nucleus X is carbon. Or it can be also that these two nuclei are in two different environments. Okay, so the environment, because of the environmental difference, these two nuclei are acting as two different nuclei. So the nuclear Overhauser effect arises due to cross relaxation between the two spins. So the nuclear Overhauser. So in our earlier questions also, we have seen that this NOE is because, okay, is the net effect is we get it from sigma, which is equal to omega 2 minus omega 0. Okay. So this is known as what? Cross relaxation. Cross relaxation between the two spins. Between the two spins A and X. Okay. So we need to, while saturating the spin, the polarization gain by steady state NOE is. Okay. So the NOE enhancement eta. So the NOE enhancement eta for nucleus X when the A nucleus is saturated is given by, we have already, this equation has already been taught you in this week's lecture. So it is given by eta equal to gamma A by gamma X into, this is the cross relaxation uh, between A and A, sigma AX and R1X. So what are these? Gamma A and gamma X are the gyromagnetic ratios of nuclei A and X. Sigma AX is the cross relaxation rate between A and X nuclei. R1X is the longitudinal relaxation rate. Longitudinal relaxation rate, or it is the reciprocal of the T1 relaxation, the spin lattice relaxation of nucleus X. So the key point is that the NOE enhancement. So this NOE enhancement is proportional to the ratio of the gyromagnetic ratios of the two nuclei, that is gamma A and gamma X. Okay. So from this equation, we can clearly state that this enhancement is because of this factor, which is the ratio of the two gyromagnetic ratio of the two different nuclei, of the two nuclei A and X. Okay, A and X. Okay. A and X. So why is it proportional to uh, the ratio between the gyromagnetic ratio of A and X? So the gyromagnetic ratio gamma determines how strongly a nucleus interacts with the magnetic field and how it couples to other spins via dipole-dipole interactions. So we have already learned about this gyromagnetic ratio in our earlier classes. So the gyromagnetic ratio that tells how much sensitive a nucleus is. Okay, and that sensitivity comes from how well it interacts with the external magnetic field. So if the gyromagnetic ratio it is having a high value, then like in case of hydrogen, in case of a proton, the gamma is high, is very high. In that case, we see that proton, that nucleus to be very sensitive because the energy difference between hmm, the energy difference between the two spin states, the higher spin state and the lower spin state, that is significantly significantly higher in case of sensitive nuclei. In case of nuclei with high gyromagnetic ratio. So this gyromagnetic ratio this tells how well it interacts with the magnetic field and also how it couples to other spins via dipole-dipole interactions. Now, in an NOEA experiment, if the nucleus A is saturated, the cross relaxation between A and X leads to a change in population levels of X, which alters the signal intensity of X. So due to this dipolar coupling between these two nuclei, so if say the nucleus A is saturated, then there will be, due to this dipolar interaction, there will be a change in the population levels of X. And therefore, we will see a difference in the signal intensity of X. Okay, so the equilibrium intensity and the intensity after the perturbation, those two intensities will differ. Now, the efficiency of this transfer of magnetization and thus the nuclear Oberhauser effect depends on the relative gyromagnetic ratios, gamma A and gamma X. For example, in case of proton carbon, okay, so say in case of proton carbon system, so this is A and this is X. Since the gyromagnetic ratio of a proton is much larger than carbon, the NOE enhancement is larger and positive when saturating the proton and observing the carbon. Okay, NOE. So basically, the difference that we will be seeing in the signal is that there will be a large change in the say signal intensity. So if the saturating RF pulse that is applied to the proton, because of the large difference in the gyromagnetic ratio of the hydrogen and carbon, the perturbation will cause a significant difference in the will cause a high difference in the signal intensity. Okay. Hmm. Right. Okay. So suppose this was the intensity of C13. So say this was the intensity of C13 at the equilibrium condition when this saturating pulse was not applied. But after the NOE experiment, we will see that the intensity of C13 signal that has increased. Why has it happened? Because the carbon is coupled to the hydrogen. Carbon is coupled to the hydrogen, and due to the NOE experiment, the nuclear spin energy that has been transferred, the polarization or the magnetization of the hydrogen has transferred from hydrogen to carbon. And because of this transfer, there is an enhancement of the signal in carbon 13. Okay. So the more the difference in the gyromagnetic ratios between the two nuclei, the more change you will see in the signal intensity. Okay. So for example, if instead of hydrogen and carbon, if say the coupling had been between carbon and nitrogen, then what would have been the case? Carbon and nitrogen. Then in that case, we would not see a much enhanced signal of carbon, of nitrogen. Okay, because we know that carbon is four times lower. The gyromagnetic ratio of carbon is 4 times less than that of hydrogen, and nitrogen gyromagnetic ratio is 10 times lower than hydrogen. So these two, the gyromagnetic ratio of carbon and nitrogen, they are not, they do not vary much. They do not vary much. So that's why the signal that we will see, that won't be an enhanced. There won't be a very uh, good enhancement in the signal difference because of the NOE experiment. Okay. So next we will next question is question 4. So what is it saying? So the question is, in an AX system, transfer of polarization from A spin to X spin is a selective population inversion experiment requires. Okay. In an AX system, transfer of polarization. Okay. So in an AX system, transfer of polarization from A spin to X spin in a selective population inversion experiment requires. So these are 4 options. So what is happening? So there is, what we are trying to do, we are trying to achieve a transfer of polarization from A spin to X spin. And how we are trying to achieve that? Through selective population inversion experiment. Okay. So what does it require? So these options are there. So first option is selective inversion of the X spin transition. Next is selective inversion of A spin transition. Selective inversion of one of the A spin transition. Or selective inversion of one of the X spin transition. So which will be the correct option? The correct option will be C, right? Why? Because let's try to understand this. In a selective population inversion experiment, okay, in an AX spin system where A and X are two different nuclei or heteronuclear spin system. Okay, say for example, uh, the heteronuclear system that we are considering, it is hydrogen and carbon. Okay, hydrogen and carbon heteronuclear spin system we are considering. So here the goal is to selectively invert the population of one of the spin transitions of the A spin in order to facilitate polarization transfer to the X spin. Okay, that is what we try to achieve through selective population inversion experiment, right? So we try to invert the population of one of the spin transitions of one of the nucleus, and through the inversion, we try to achieve polarization. We try to polarize the another nucleus to which it is coupled. So say it is the X nucleus. So in an AX system, the A spin has 2 transitions corresponding to its coupling with the X spin. One when the X spin is in its alpha state, and another for when it is in its beta state. Okay. So we know that in the nuclear spin has two spin energy states. One is the alpha and one is the beta. Okay. So selective inversion of one of the A spin transitions. What does this mean? So this involves inverting the population associated with just one of these transitions. Okay. So rather than both. So it will be either inverting the population transition from alpha to beta or beta to alpha. Okay. Not both. Only either we'll try to invert the population that is existing in the alpha spin state to beta, or it will be from beta to alpha, not both. Okay, by doing this, you specifically altered the population difference for one of the A spin transitions. Okay, like earlier we were trying to understand, like in the NOE, positive NOE and negative NOE, that each spin system can have two spin transitions, A1 and A2, right? Similarly, X can also have X1 and X2. Okay, so A1 is when the transition is from, say, alpha to beta, and A2 is when the coupled system from this is when the transfer is from alpha alpha to, say, beta alpha, and A2 is when the transition is from alpha alpha to beta beta. Okay, so these are the two transitions. So by doing this, you specifically alter the population difference for one of the A spin transitions, which creates a non-equilibrium population distribution between the spin states. Non-equilibrium. So due to the perturbation, due to this perturbation, there is a change in the population in these energy states. And this population uh, change, that the population that exists due to the perturbation in these energy states, that is different from the population that was existing earlier at the equilibrium condition. So now, due to this, how is the polarization getting transferred? So when one of the A spin transitions is selected, is selectively inverted, it changes the population distribution in such a way that polarization can be transferred to the X spin. In such a way that the polarization can be transferred to the X spin. Okay. In that way, we will try to perform the experiment. So this selective inversion leads to an imbalance that, due to the coupling between A and X, results in polarization being transferred from A to X. So this selective inversion that causes an imbalance in the population. And because this A and X are coupled to each other, so this results in the polarization being transferred from A to X. Okay. Okay. So we'll resume again. So, uh, okay. So the next question is, uh, so the population transferred. Okay. So the next question is, so the population polarization transfer in an SPI experiment results in selective inversion of the X-spin transition. Differential transfer of magnetization, net transfer of magnetization, positive and negative signals in the spectrum, all positive signals in the spectrum. So why does this selective inversion happen? Inversion of the experiment. Is it because of differential transfer of magnetization or net transfer of magnetization, positive and negative signals in the spectrum, or all positive signals in the spectrum? So choose the correct answer. So the correct answer here is D, right? A and C. So why is it so? So it is because of the differential transfer of magnetization and positive and negative signals in the spectrum. So we'll try to understand this. In a selective population inversion experiment in NMR spectroscopy, the polarization transfer is a process where magnetization is transferred from one nuclear spin. This transfer from one nuclear spin to another through their interaction. So the nucleus from which the transfer is happening, that nucleus is referred to as the donor nucleus, donor spin. Okay. And the nuclei to which the polarization is transferred, that is called the acceptor spin. And because of the interaction that is there between the two nuclear system. So the results of this transfer can manifest in different ways in the NMR spectrum. Okay. So what is this differential transfer? Because this is a result of the differential transfer of magnitude. You need to understand what is the differential transfer. So in an SPI experiment, selective inversion typically affects only one transition, leading to a difference in the population levels between spin states. So this differential effect can lead to a situation where some magnetization is transferred from the donor spin to the acceptor spin, while other parts remain unaffected. This leads to an unequal distribution of magnetization. This leads to an unequal distribution of magnetization, known as differential transfer. This the results of this differential transfer is that some peaks in the spectrum may be enhanced while others may not, depending on the specifics of the polarization transfer and the coupling constant. So depending on these two specifics of the polarization transfer and coupling constant, the polarization transfer will take place. So so what are these positive and negative signals? There will be positive and negative signals because why? Because of the differential transfer of the polarization. So due to the nature of the differential polarization transfer in this experiment, the resulting signals in the NMR spectrum can be either positive or negative, depending on the phase. Okay, depending on the phase of the signal of the donor, the transfer can be either positive or negative. The net result of the NMR spectrum that will be finally seen, that can be either a positive signal or a negative signal. Okay, and it depends on the direction of the transferred magnetization. If the polarization transfer inverts the phase of the signal, this can lead to the negative signals in the spectrum. So if the polarization transfer which is taking place from one of the nuclei of this A to X, if that transfer results that transfer leads to an inversion of the phase of the X nuclei, then that will lead to negative signal. Okay, while direct polarization, if there is direct polarization that takes place, then that will typically result in positive signals. Okay, so the mixture of positive and negative signals, mixture of these positive and negative signals is characteristic of differential polarization transfer and is often observed in NOE and SPI experiments. Okay. So the net effect of the transfer of this positive and negative signal, that net effect is what is seen in the NOE and SPI experiments. Okay. So next we'll be looking into the concept of rosy. Okay, so this concept has also been discussed in this week. So we'll try to get a brief understanding of what this rosy is, and then we will look into some of the questions that have been that you might get in this week's assignment. Okay, what are the basic concepts? So if we start from the very basics, then this NMR, as you all know, it is a technique that exploits the magnetic properties of certain atomic nuclei. So when it is placed in a magnetic field, nuclei with a non-zero spin, like for example, a proton or carbon, align with or against the field. By applying radio frequency pulses, these nuclei can be excited to higher energy states. When these nuclei, which are in the higher energy state, they relax back to equilibrium, then they emit radio frequency signals. And the emission of the radio frequency signals while returning back from higher spin state to lower spin state, that signal is detected. That signal is detected by the detector, and then it is analyzed to provide information about the molecular structure of the nucleus uh, of that particular system, okay, of the particular sample. So there are during the relaxation process, okay, during the relaxation process, that means when the spins relax from the higher energy spin state to the lower energy spin state. So that can be brought about by that relaxation can be brought about by two processes. Okay, so first is the T1 relaxation, or it is also known as longitudinal or spin lattice relaxation. So in this relaxation process, energy is transferred from the spins to the surrounding lattice. Okay, the spins of the nuclei which has been excited because of 1 minute. Okay. Uh, so okay, so this can happen by the relaxation process can happen by two means. That is the T1 relaxation, or it is also known as longitudinal or spin lattice relaxation. So here the nuclear which has been excited by the RF pulse that gives away its energy to the surrounding lattice while relaxing to the equilibrium state. Whereas in case of T2 relaxation, which is also known as transverse or spin relaxation, the relaxation happens by loss of the energy to the neighboring nuclei, to this neighboring nuclei uh, nuclear spins. Okay. So the polarization transfer refers to the process where the polarization of one nuclear spin is transferred to another nuclear spin. So its surrounding nuclei, it loses the nuclear spin, and in that way it relaxes to its equilibrium state. So that type of relaxation is known as T2 relaxation or transverse or spin relaxation. And another is what is known as cross relaxation. So when is it that we see? So this happens when two nuclei are spatially close. They can influence each other's relaxation, leading to a phenomena known as cross relaxation. So when two nuclei are spatially close to each other, then they can influence each other's relaxation. And this this is what leads this way of relaxation is what is known as cross relaxation. So this is the basis for your nuclear Overhauser effect in nosy, and ROE, rotating frame Overhauser effect in ROSE. So what is this Overhauser effect? So in nosy or nuclear Overhauser effect spectroscopy, cross relaxation occurs due to dipolar interactions. This we have already seen. Okay. So due to the dipolar interactions between the spins, the we see this nuclear Overhauser effect. The nuclear Overhauser effect depends on the molecular correlation time tau c, leading to either positive or negative enhancements depending on the size of the molecule. So the molecular correlation time tau c, it is dependent on the size of the molecule. Okay, and because the size of the molecule will determine whether the molecular correlation time tau c, it will be either positive or negative. that will give either a positive enhancement or a negative enhancement. Okay. So this is a diagram, pulse sequence diagram of a Rosé experiment. Okay. So let's try to understand this. So what happens is magnetic field and RF pulses. A sample is placed in a strong magnetic field aligning the nuclear spins. And RF pulse, so when the sample will be subjected to the strong magnetic field, then most of its nuclear spins will align along with the external magnetic field. Now, an RF pulse is applied to excite the spins. And then, because of the application of this RF pulse, that will cause the flipping of their transverse plane, flipping them into the transverse plane. So, spin lock. In Rosie, a spin lock pulse is applied after the initial radio frequency pulse. So, this pulse keeps the spins aligned in the rotating frame, allowing the study of cross relaxation between nuclei. So, what will this spin lock pulse do? So, this pulse will keep the spins aligned in the rotating frame. Okay, and that will enable us to study the cross relaxation or ROE between nuclei. Now, then we will allow mixing time. So during this spin lock period, or that this is also known as mixing time, cross relaxation occurs. Protons that are close in space will interact, leading to cross peaks in the spectrum that indicate spatial proximity. So how will the detection take place? After the mixing time, the RF pulses stop and the NMR signals are detected as the spins relax back to the equilibrium. Okay. So this is the overall experiment of Rosie. So based on it, we will try to answer one of the questions that is related to this concept. So the question is, in the 1H Rosie experiment, these are the options. So the options are: the enhancement is always negative, the enhancement is always positive, the sign of ROE is positive for small molecules and negative for large molecules. Or another is the sign of ROE is positive for large molecules and negative for small molecules. So the answer here is B. The enhancement is always positive. So to solve this question, you need to understand the relationship that exists between the molecular correlation time and the sign of the rotating Oberhauser effect in Rosie experiment. So and we also need to understand molecular correlation time. So the correlation time is related to the size and dynamics of the molecule. So small molecules typically they will have short correlation time. Short correlation times because you will see fast tumbling in case of small molecules. While in case of large molecules, they have longer correlation times or slow tumbling. So what is the row mechanism in Rosie rotating frame Oberhauser effect? So for small molecules with short correlation time tend to have a positive nuclear Oberhauser effect. Okay. So small molecules with short correlation time will have a positive nuclear Oberhauser effect. But in Rosie, the ROE is also typically positive. For large molecules with longer correlation time might exhibit a negative nuclear Oberhauser effect. But in Rosie, the rotating frame Oberhauser effect remains positive due to the nature of the rotating frame mechanism. So the sign of the row, what will be the sign of row? The row in a Rosie experiment is generally positive regardless of the molecular size or correlation time. So this is the distinguishing feature of Rosie compared to Nosy, where the nuclear Oberhauser effect can be negative for large molecules. So unlike nosy, where the no this nuclear overhauser effect can be negative for large molecules. In case of rosy, uh, the enhancement is always positive. Okay, so given this information, the correct answer to the question is B. The enhancement is always positive because in a rosy experiment, the rho is typically positive for small and large molecules. Molecular correlation time. The correlation time is related to the size and dynamics of the molecule, right? So for small molecules, they will tend to have short correlation time to have a positive NOE, but in rosy, the rho is also typically positive. But for large molecules with longer this tumbling time or correlation, yeah, large molecules with slow tumbling or longer correlation time might exhibit a negative nuclear overhauser effect. But in rosy, what will happen here also? We will see a positive. It will remain positive due to the nature of the rotating frame mechanism. So because of the rotating frame change, irrespective of small molecule or large molecule, the effect is that it will the sign of the row is always positive. So the sign of ROE in a rosy experiment is generally positive, regardless of the molecular size or correlation time. So this is the distinguishing feature of rosy compared to nosy, where the nuclear overhousing effect can be negative for large molecules. But in case of rosy, the rho is positive irrespective of whether the molecule is small or large. Okay. Okay. So that's it for today's this week's uh, tutorial session. So we'll stop here, and I hope that you will be able to answer the questions that you will be getting in this week's assignment. So all the best. Bye.